Okay. Then also a warm welcome from my side to everybody listening to this presentation. Our presentation is entitled Measurement and Analysis of Disturbances Induced by Electric Vehicles, a case study. We are presenting preliminary results today, so they are coming in quite hot. So it's we just measured this and we are still finishing up the reports and the interpretation on these measurements, and you can now so to speak, participate in that. Let me give you a quick outline of what I will be talking about today. I will just do a short revisit of the harmonic power flow measurements with PQMS. This was the topic of our last presentation in March this year. Then I want to present the case, the measurement setup, our measurements, and then I want to draw a first conclusion as far as we can already conclude this topic. Okay, just a short revisit. We introduced last time this power quality measurement system, or PQMS. The aim of this PQMS was actually to provide a very high resolution in time and in frequency, very high resolved signals for spectral analysis of current and voltage, and to perform harmonic power flow analysis. So last time I was presenting the measurements of a cooling machine in a building, where we analyzed the current draw and the voltage. And this was our voltage signal. We can depict everything period-wise, so we can perform spectral analysis consecutively over several periods that we are obtaining in our measurements. This was the current waveform that I was presenting the last time. Therefore, we could very accurately perform the magnitude and phase spectrum without any spectral leakage error induced by harmonics. This is actually the goal of this power quality measurement system. So to speak, we have a high time resolution in the spectral data. So since we can use a single period for spectral analysis, or 2 periods, depending on the windowing that we perform, we obtain very much one spectrum per fundamental mains cycle. And we use that for the harmonic active power and impedance measurements. So in this example, this was the spectrum of the active power on this machine on L1. And the great thing is that we can distinct between positive active power, this is power consumption by the device, and we can distinct negative active power, this is power injection by the device. So here we have devices that perform as a power consumer on the fundamental period, on the fundamental frequency, for example, but they become a power generator on harmonics. Okay, now let's switch to the case I want to talk about today. In summer this year, one medium-sized IT company approached us. They have the problem with their electric vehicles, and if we could go there and measure and try to sort out their problem. This company has its own office building, and this office building is connected to the low voltage grid with no other participants. So this is the only building in this low voltage grid. So to speak, they have their own transformer to the medium voltage grid. This building is now equipped with 4 electric vehicle charging stations, and they are connected in 2. They have 2 charging stations per string, and there are 2 strings coming out of their low voltage distribution in the building, in the basement. And each of these charging stations has 2 charging ports that are able to charge at 22 kilowatts with AC charging. The maximum power that can be drawn per string is 44 kilowatts. So if you have 4 electric vehicles connected to those 2 charging stations in one string, you can actually charge only at 11 kilowatts per charging port, so per car. And additionally, this building has 15 kilowatts peak of installed photovoltaic generation on its roof. And I want to talk about the EV charging conditions. This company leased 14 small electric vehicles of French origin for their employees, and they use them as their private cars, and they are charging them mostly on that building. As I already said, we have 2 times 2 charging stations of 2 outlets of 22 kilowatts each, and along one string, these charging stations are configured as a master-slave configuration. So the one master station determines how much of power output is given to each charging port. So in total, in sense of the total power consumption of electric vehicle charging in this building, we have at maximum 88 kilowatts of maximum total charging power. So what's the problem with this EV charging? Well, if there is, in normal working conditions, if there is no electric vehicle charging, there are normal working conditions in this building and everything is fine for the employees. As soon as one electric vehicle is connected to one of these charging stations, it doesn't matter which one it is, devices in the office building start to emit a high-pitched buzzing sound. With an smartphone audio spectral analyzer, we could see that is approximately at 10 kilohertz, this sound. And everything is starting to emit this sound, especially monitors in the offices and lights. So the lights on the ceiling and the monitors. And they have no clue what is causing that. They can correlate it with the EV charging. And they are helpless. They do not know how to solve this problem. They found out that if you use certain manufacturers of monitors and certain manufacturers of lights, then you can actually reduce this noise emissions a little bit, but it's all not very good. The biggest problem is if there are 2 or more EVs charging, then this high-pitched buzzing sound starts to oscillate with a frequency of about 0.5 to 2 hertz, depending on which electric vehicles are charging there. So the CEO of the company came to us and he told us, I have an influence on the well-being of my employees in the workspace, and I have a lot of productivity as soon as these EVs are charging. The problem is most of these employees, they have no access to their own charging stations at home, so they have to charge their vehicles at work. And that's what all this was intended for. So they need to solve this problem. The problem is the EV manufacturer denies any responsibility and told the CEO that the cause of this problem would be the charging station itself. So we went there and we came with our power quality measurement system and we started to set up measurements. We measured in the low voltage main distribution room in different configurations, and we measured in the at one of these charging stations. And what I want to show you now is what are the first results, the preliminary results of our measurements there. At first, we looked at the power grid in idle. So there is no electric vehicle connected to any of these chargers, and there is no noise emission in the rooms. And so we want to see what's the power grid, what's the voltage looking like. So we measured in the low voltage main distribution room in the basement. And as you can see, the waveform of this voltage is, it's nothing spectacular. It's not perfectly sinusoidal. We have some low grade harmonics. But if you look into the spectrum, and in this presentation, I just cut out the spectrum from 0 to 12.5 kilohertz because that's where the music is, so to speak. We see that we do not have any oscillations at 10 kilohertz. So there is no noise emissions at this frequency range, and it is we see we have something at the L3 to neutral voltage at around 4 kilohertz. And now there is the benefit of our power quality measurement system coming into play, because how did we obtain this spectrum? The spectrum is actually the average of all the spectra that we obtained during our measurements. And since this presentation is this 2D plot is this is quite static and you cannot see any dynamics, we want to switch to another presentation of voltage, current, and power signals, which is a form of a heat map. And if I change to this heat map, you can actually see this frequency component on the L3 to neutral voltage over time. So let's switch over. And I want to just give you a short introduction into this, chart. So at the vertical axis, we have the frequency from 0 to 12.5 kilohertz. And the white line you see at the top of this chart is actually the fundamental component, the 50 hertz component. At the horizontal axis, we have the time. So this is the duration of our measurement, which was 30 seconds in this particular measurement. And the color scale is indicating the actual magnitude of the voltage. So, and we get one time point for every fundamental period. So approximately 20 points per second, 50 points per second. one every 20 milliseconds. Now we can compare the L1 to neutral voltage with the L3 to neutral voltage, and we see that we have at approximately 4 kilohertz, we have some of these emissions, we have some disturbances there. Since it is only single phase and this is an office building, we assume that it is some switching or power supply or something like that, or some lights that are emitting these disturbances. Nothing of interest compared to this what's coming now when we look at the EV charging. So now we started with the electric vehicle charging. We connected one electric vehicle to one of these charging stations, and we were measuring in the low voltage distribution room. And now we have also current signals. And this is the current drawn by this one vehicle charging. You can see it is highly distorted. We have low order harmonics, and we have some high frequency disturbances on the currents as well. Now, when we look at the RMS current over time, we can see that the current was reduced at around 10 seconds into the measurement, nearly to 0, and then it came back up again. This is something that these electric vehicles did quite a lot. They reduced their charging current or stopped charging at all, and then came back very fast again. And it was a hot summer day, and they actually turned on their cooling. So their ventilators were starting to run. And during this time where the ventilators started to turn on, they stopped the charging process nearly entirely. So with this highly distorted current signals, we can now have a look at the L1 to neutral voltage and the L3 to neutral voltage. And we can see that we have quite significant distortions and signals in the range of approximately 10 kilohertz, which is exactly the range where we have this acoustic emissions in the office building. And you can also see that around 10 seconds, these emissions shortly stop or are attenuated very much. This is where the EV stopped the charging process for a very short moment and came back up again. So we can here correlate these noise emissions and these distortions on the voltage signals with the actual charging process of the vehicle. We can also perform a calculation of these heat maps with the current. And we can actually see that we have this, we have quite some clean current when we come to this short reduction in power draw at around 10 seconds into the measurement. So now we have the current and we have the voltage period-wise. We have the spectral components and we have them with a very precise angular and amplitude information. So we can now perform the active power calculation as I was introducing the last time before. And we can now actually see that we have power draw at the fundamental component. This is the significant power draw. This is actually the where it was supposed to be the power draw. And we can see that we have some power flow at around 10 kilohertz, where we have exactly these noise emissions. In these charts, in these heat maps, due to the logarithmic scale of the power, you cannot see the sign of the power flow, so the actual direction in which the power is flowing. The great thing is when we perform this active power calculation on all 3 lines, we can actually add them up and come up with a total active power consumption. And here we see that we have approximately 21 to 22 kilowatts of power draw in total at the fundamental components. And we can calculate this power flow that is coming here in at around 10 kilohertz. And now I want to go into the time signals and want to show you these actually frequency components over time. And when we have a look at the fundamental power, the total active power on the fundamental component, we can see that we charge at very constantly at 21 kilowatts over time. At 10 seconds, the charging process is stopped entirely. It goes back to 0 kilowatts and then comes back up in approximately 2 seconds again. This is the active total power on the fundamental, and this is what the charger is supposed to do. This is approximately the nominal charging power of the charger. Now we can have a look at the total active power around 10 kilohertz, where we have these noise emissions. We can see that there is a negative active power emission. So this is an emission of active power back into the grid, and this has to go somewhere. So this is actually the active power that we think is going into all these devices that are starting this high oscillating, this buzzing sound. What we can also see is, as expected and as we saw in the heat maps before, that these active power emissions at 10 kilohertz stop entirely during this stop of the charging process. Okay, now I want to show you another interesting measurement. This is actually 2+1 EVs charging. So you can see the red circle in the graphic. This is where we actually measured at the charging station itself with 2 connected electric vehicles. And there was a third electric vehicle connected to another charger at the other string of this installation. We had no influence on that EV charging. This was a very angry employee that came to us and said, "Hey, I have charged my car. I want to be able to get home." So he plugged in his car and he just charged it. So we had the influence of this EV. This is why I say 2+1 EVs charging. But the results are quite interesting. Let me show you the L1 and L3 to neutral voltage. And you can actually see that there is quite a dynamic in these distortions at around 10 kilohertz. And you also have these distortions in the current. And you can see in the current especially that you have 3 short-timed changes in the spectrum that is influencing the entire spectrum. This comes from the second electric vehicle that we were charging, which stopped the charging process and 2 times started to turn it on again. And at the 3rd time, so approximately after 110 seconds here, it started the actual charging process itself. And it's very interesting what we can see here. Let me show you the total active power flows. So you can actually see that in the first couple of seconds, the first 25 seconds, we have quite a constant power flow at 10 kilohertz. And then when the second vehicle tries to enable its charging, show you the laser pointer, when the second vehicle starts its charging process very shortly, you have actually a reduction in these noise emissions, what you can see from this chart. And when the vehicle starts its charging process entirely, then you can see we have these oscillations that we also have in these noise emissions. So let's have a look at the total active power on the fundamental. You can see here that it is charging at 21 kilowatts. When the one vehicle is charging, you can see these 2 spikes where the second vehicle is actually starting to charge, stopping it again. We do not know why it did that. And then at the 3rd try, at approximately 110 seconds, it starts its full charging process, and we double the charging power at this particular charging station. Interestingly, now we have a look at the total active power around 10 kilohertz. We can also see we have negative active power emissions. And let's have a look into the first couple of seconds where the one vehicle was connected to the charging station. And here we can see it's actually these oscillations I was talking about. As soon as 2 electric vehicles were charging, the car, it started to oscillate at around -9 watts. And this is actually due to the emissions on the voltage coming from this +1 vehicle that was connected to the other charging station at the end of the other string, which actually shows that these emissions are propagating quite far into this low voltage grid. When we have a look at the point in time where all vehicles were charging, we can actually see this additional 3rd vehicle coming in and these 3 oscillating around each other. So there is kind of an 3-fold oscillation beat around these active power emissions at 10 kilohertz. That's actually it. I'm now eager to hear your opinions or discussions on that. Preliminary conclusions that we can draw is the EVs are definitely the cause of these disturbances. The charging stations themselves are not part of the problem because they are just a switch that closes and connects these electric vehicles to the power grid. Of course, there is some communication via a separate communication channel, a pulse width modulation channel between the charging stations and the electric vehicles, but mainly these charging stations are just a switch that connects the 3-phase AC power to the car itself. The PQ disturbances are cause of these noise emissions. That is also what we can directly correlate. And as I said, the charging stations themselves are not part of the problem. Okay, that's it from my side. Thank you very much for your attention, and we are eager to hear your questions on this topic.